Welcome to Rails World, everybody. I'm so happy to be the first person to welcome you to Rails World. Yesterday I learned something really interesting, and that is that if you use a specific color, like a green color as the background on your slides, it becomes transparent like this. Yeah, isn't that cool? Yeah. So like my display up here is the slide like this, but it's got a green background. So they actually key it out for you. But I wanted to do this in my slides today because I wanted to be completely transparent with all of you. Yes. Thank you. Yeah. Happy Friday. Happy Friday, everybody. Say happy Friday, please. Yes. It is always Friday somewhere, and today it is Friday here, and I'm very happy that it is actually Friday. The sad thing is, though, today I'd planned out my keynote in advance, done all this work. I was going to talk to all of you about system tests today using my Macintosh. But since I can't do that today, today I'm going to talk to you about David's keynote. I really enjoyed David's keynote. Now we all know how much David thinks about the Roman Empire. I'm also really excited about the new framework Action Push. That seems really exciting, right? Yes. Very exciting, but I'm going to let you all in on a little bit of inside baseball. It wasn't actually originally called Action Push. It was actually originally called Action Push Native. Like, that was the original name. But the rest of us on the core team, we didn't really like that name so much, so we gave David some active pushback. But the thing is, when it comes to active push, when active push comes to action shove, David can be a reasonable person, so he renamed it, and I appreciate that. I also enjoyed David's presentation about omachi, and I hate to correct him on stage. Never mind. I love to correct him on stage. It's actually GNU/omachi. Just. Anyway, I really didn't have David growing a neckbeard on my Rails World bingo card this year. Yes. I was also excited about 30,000 assertions in 2 minutes. That's really wild, right? But I mean, come on, please. I know how to beat this. I can easily beat this, so I want to give a demonstration to you. This is intense. Right here, we're going to beat that number. I have a test right here. Let's go. So we're going to do 30,001 assertions. Yeah, look at that, using mega test. Look at that, 10 milliseconds. 10 milliseconds, yes. And this was all done on my slow, old MacBook Air M4. Ugh, terrible. Anyway, my name is Eric Patterson. Hello, everybody. I'm on the internet. My name is Tenderlove. I've been on the Ruby core team since 2009, and I've been on the Rails core team since 2011. I don't know how many of you are here this morning, but it is true, I do speak Japanese. And I want to give a very short lesson. I'm going to teach you all a handy phrase today. The phrase is "shōshō omachi kudasai." And what it means is, can you wait a little bit, please? And you'll hear this all the time. What David didn't know is that omachi is super duper popular in Japan. Really popular. You'll hear this phrase when you go to restaurants, when you go to hotels, everywhere. So I want to teach you another phrase too. What if you're going up to somebody and you say, "Hey, I'd like to have a little omachi, please. Can I have that? I would like to try out this operating system." You can say exactly the same thing. "Shōshō omachi kudasai." That is how you would say it. I work for a senior staff engineer at a mom and pop startup called Shopify. Small company. Hopefully you've heard of us. We use Ruby and Ruby on Rails. I think we run probably the biggest Rails app in the world. Now, unfortunately, I didn't really know how to measure that. Like, how do you measure what is the biggest app in the world? So the way I decided to measure it was by font size. And indeed, we have biggest Rails app in the world. Since today is Friday, and this is the last talk of the conference, I thought we would try to have some fun and talk about some very, very light topics. So I hope you're all excited for that. I'm just kidding. We are not going to do that. Today we are going to have a very, very technical presentation, and I apologize. I know for some of you, you're happy because this means the end of the pun section of my presentation and onto the technical section of my presentation. But like, why am I doing a technical presentation? The reason is mainly because I love programming. I love programming a lot. I like to do it as my hobby, and I also get to do it as my job, and I just really love it, and I'm excited about the things that I work on. I'm very excited. Yeah, slide. There we go. I'm very excited, and I'm really excited to share the stuff that I've been working on with my team at work. So that's what I want to talk about today, is mainly work stuff. So today I'm going to talk about work stuff, specifically the stuff that my team has been working on at Shopify, and how it's going to improve our lives and your lives, as well as some pro tips for Rails developers. At Shopify, I'm on the Ruby and Rails infrastructure team, and you may be surprised to learn this, but we work on Ruby and Rails and infrastructure. So we are the Ruby and Rails infrastructure team. Our team's kind of, I don't know, we work on a lot of stuff, but I want to give you some context around the work that we do, and a big goal of ours is to improve machine utilization at work. So we want to work on performance, and that helps us improve machine utilization. And I want to make that a little bit more concrete and give you an example from work of the kind of things we're focusing on. And I want to do this to provide context for the work that we do inside of Ruby and Rails. So one of the things that we want to do is we want to increase, when I say improve, improve productivity, we want to increase the number of, the amount of parallel work that we do on a machine, but we don't want to increase latency. So for example, we want to service more requests, but we don't want to destroy latency for anyone. So we want to improve the amount of parallel work that we're able to handle anywhere. And I'm careful not to say requests necessarily, because we're really talking about parallel work. It could be web servers, test suites, whatever. We just want to get more work done on a machine, but we don't want to degrade latency for anybody. And to make these terms a little bit more concrete, we have a very large application at work that has a very, very unpredictable workload. And unfortunately, what this means is when we get a request coming in, we don't know whether that request is going to be I/O bound or whether it's going to be CPU bound. We don't really know that. And what this means is, let's say we have a web server, a process-based web server with 4 cores. This is a mom-and-pop startup, so we can only afford 4 core machines. Let's say there's 4 cores, and we know that some of the requests are going to be I/O bound, and we know that some of them are going to be CPU bound, and we want to utilize this machine as much as possible. So what we'll do is we'll fork off, say, 1.5 times the number of processes. So we'll have 6 processes on our 4 core machine. We'll pre-fork them. So each process can only handle 1 request at a time, so we can handle 6 requests in parallel. But I want to consider 2 extreme cases. Let's say we get 6 requests coming in, and they're all doing I/O-bound work. So if that happens, all of these processes are basically doing I/O stuff. I don't know, writing to a database, doing whatever. And our CPU utilization, our CPUs aren't doing anything at all. This is kind of a bummer because our web server could take on more work, but it's not. We're not processing any more requests. So now let's consider the other end of this spectrum. Let's say we get 6 processes coming in, or 6 CPU-bound requests coming in. Now we have 6 processes that are all fighting over 4 CPUs. So unfortunately, this impacts our latency, and we don't like that either. This ends up increasing latency because we have noisy neighbors. They all want to get some time on the CPU, so some of them have to be scheduled off the CPU, and that's just not good for our end users. And a side note, like I want to go on a little bit of a side note, this impacts all web servers. This isn't just process-based web servers. It's also like Falcon, Puma, whatever. And the reason this happens is because we only have one construct in Ruby for doing CPU Bound Parallelization, and that's processes. We can only run code in parallel on processes. It's the only way we can do it. And I want to show a little bit of demonstration here. So let's say we've got two examples. We're going to calculate a Fibonacci sequence because that's what we do at work. Fibonacci sequence. There's going to be a lot of this in the presentation. We're going to do it just sequentially versus threads. So we'll do one just straight line, and we'll compare it to threads. If we do this on my lowly MacBook M4, we get it done in about 2 seconds. If we do the same example using threads, unfortunately, it takes the same amount of time, 2 seconds. So we didn't get any parallelization, 0. Now, let's compare that again to fibers, for example. We use an async framework. Again, 2 seconds is our baseline. If we run this example with async, again, 2 seconds. We're not doing any better than before. Fibers will take the same amount of time. Let's do this again, but this time we'll use processes. So of course, linearly will take 2 seconds. If we run this with processes, on my machine it was about 480 milliseconds, around there. So we're actually seeing some parallelization here. We're getting some time. So let's return to web servers now for a minute. What we'd really like to have is we'd like to have a load-aware web server where, for example, let's say our first 4 requests come in. They get scheduled to these different processes. Let's say all of them are I/O bound. That's what happens. They come in. Now another request come in. We can take those on. We'll just spin up another process and take that on because our machine isn't that busy. We can take on more. Now let's compare that to say we get a CPU bound request coming in. So the CPU bound request will come in. We start getting load on the CPU. Eventually, we start using up all 4 of our CPUs. And then when the next request comes in, we'll say, yeah, we can't take that. Let's not do that one right now. We're busy. Can you send that off to another machine? We're currently at capacity. But the question is, like, how do you do this? And this is going to be a little bit hand-wavy here. But an idea that we've talked about or we've had is to provide back pressure using HTTP 2.0. The reason we're thinking about doing this is because H2 can send information upstream asynchronously. So we can say, like, oh, hey, proxy, I'm busy. We can set max concurrent streams, for example, and say, like, I can't take any more streams right now. Please, like, send data somewhere else. So we can actually provide back pressure to the proxy. This solves the communication error between the router and the proxy and the web server, and we should be able to load balance stuff better. And this is, by the way, this is all theoretical. This is what we would like to get to. So let's say we had this. Let's say this actually existed. What if it did exist? Now, when a request comes in, I showed this before, like, what do we do in this particular case? We have to create a new process, right? We have to spin up a new process. Now, how do we do that? How do we do that? What is the code that we write to do that? One idea is, well, we could fork. We could just fork a new process in our web server and then take on that request. But the question is, like, can we fork fast enough? We don't know if that's true. Another potential answer is we could say thread.new, or we could do fiber.new, create a new thread, create a new fiber. But as we saw in the previous benchmarks, those can only handle I/O bound requests. They can't handle CPU bound requests. So what could we do? And the answer is Ractor.new. This is where Ractors come into play. We can absolutely allocate new Ractors fast enough, and they allow us to handle CPU-bound parallelization. So this is kind of the context for our team. This is what we've been working on. The stuff that I've described, these production problems, this is the things we've been thinking about. And what I want to discuss today is, like, from the language level, where we're trying to attack these problems. And we're trying to attack these problems on two different fronts. The first front is the multi-CPU performance, so multi-core performance, and that would be working with Ractors. We're hoping that Ractors will allow us to make the most efficient usage of all CPUs on the machine at the same time. But this doesn't address single core performance. For single core performance, we're working on a new JIT compiler called ZJIT. And I want to talk about both of these efforts today, Ractors and ZJIT. So first, let's discuss Ractors. This year, my team has been working on improving Ractor speed and usability in Ruby 3.5. John Hawthorne, if you've met him here at the conference, he is leading the project. And our team has been working really closely with Koichi Sasada, who is the original author of Ractors. So we're working on these. Now, you might be asking, we get this question all the time. We have a lot of concurrency choices in Ruby. Which one is the best one? We have threads, we have fibers, we have processes, we have Ractors. Which one is the best? And the problem is, if you ask, talking heads like me, what the answer is to this, they'll say, it depends. But I think this is a small dog answer. I think the big dog answer is Ractors. You just always use Ractors. Also, John made a really, really great logo for Ractors, which I want to show here. This is All right. So if you're not familiar, let's discuss Ractors. Ractors are Ruby actors, and that's where the name comes from. So it's Ruby actors, Ractors. They are basically an actor style of parallelism in Ruby, and Ractors give us true parallelism. Now, unfortunately, well, actually, no, it doesn't matter. Why did I say unfortunately? There is still a GVL. So Ruby still has a GVL, but the way that we've designed the system is such that each Ractor has its own independent GVL that they can all run independently of each other, and that means, let's do the slide. Each Ractor has its own GVL that can run independently of each other, and that means that we can get true parallelism out of all of them. So let's do our Fibonacci sequence test again. If we run this in serially, of course it's 2 seconds like you saw before. If we try this with Ractors, we'll hit 480 milliseconds. So we're able to do true parallelization with Ractors. And just to refresh your memory here, I've got a benchmark here where we're checking our base measurement versus threads, fibers, processes, Ractors. And you'll see that the first 3 are around 2 seconds, whereas if we use processes or Ractors, we can actually get down to 480 milliseconds. So again, true parallelism, the only way we can get that in Ruby is either via processes and Ractors, and we want to focus on the Ractor solution. Unfortunately, if you use Ractors today, you'll see this warning. This warning comes out, and it is a big, scary warning. And it says Ractors is experimental, and the behavior may change. And unfortunately, that's totally true. It absolutely has changed. APIs are changing, and part of the work that we want to do on the team is stabilize that API, make sure that it works well and fast. And the other thing that it says is also there are many implementation issues, and that is true as well too. There are many implementation issues. So we're trying to take on those behavioral changes as well as the implementation issues, make sure that the behavior is stable and that the implementation issues are fixed. And we're hoping that if we can do enough work on that, we can actually get rid of this message so that people will feel a lot more comfortable using Ractors in the future. So I want to talk a little bit about the behavior changes, or how to use Ractors. And this is in Ruby 3.5, so you need to be using Ruby. Either wait for Ruby 3.5 or don't. You can build it from Edge. Please do that. And we'll also talk about some implementation issues. So Ractors are very similar to threads. They're like threads, but harder to use. But in a good way, and I'm going to explain that in a minute here. So Ractors have kind of a rule with them. The rule is that you cannot share immutable objects between Ractors. That's not allowed. So we don't allow that. Ractors will copy immutable objects, and I have an example of that here. So here we have two code examples. On the left is a thread example, and on the right is our Ractor example. And all we're doing here is we're we're getting a mutable string, and this is important. We've got a mutable string here. We're pushing the mutable, or we're popping the string off of a queue. So in thread world, we'll pop it off a queue. In Ractor world, we'll pop it off a queue, but this is actually our default mailbox, what we call the mailbox for the Ractor. After that, we'll print out the object ID of the string along with the string itself. So we don't need to make a queue. One nice thing about Ractors is we don't need to make a queue. They already have default queues, so we can just push on to that default queue. If we run this code, we'll see here on the threaded side, the object IDs are identical. There was no copy. But if we look on the Ractor side, we'll see that the object IDs changed, and that's because we actually duped the string when it crossed the boundaries. So when that string went from one Ractor to the other, we ended up copying the string. So we're not allowed to share mutable objects between Ractors. If we change this code, so we just add, where is it? Frozen string literal here, true at the top, the thing I was complaining about this morning. If we add that at the top, we'll see that actually the object IDs are identical. So as long as the objects are immutable, we can pass references between Ractors, and it doesn't matter. It's fine. There's no copy. So how do we make immutable data? I already showed one example. We can have frozen string literal true, or we can freeze an object. But unfortunately, that's not going to work if we have like a deeply nested object. Like, let's say, for example, we parse some JSON. We got a big old JSON hash out of it. In that case, we can use ractor.makeshareable, and that will deeply freeze the object's data structure. Or like some libraries, like JSON, will provide APIs that give you back frozen data structures already. So in this case, you can pass like freeze:true into JSON.parse, and the data structure that comes back out of JSON parse will already be frozen. So you can pass that between your Ractors without copying. So communication, how does that work? Like, we know how to make immutable data, but how do we communicate between Ractors? Ractors use what is called a port, and this is in Ruby 3.5 again. Ports are basically a queue, and we can use them. We use them like this. Every Ractor has a default port. These two bits of code are actually exactly identical, except that rather than calling ractor.current.default port, and receive on that, we can just call Ractor receive. So one is shorthand for the other. These two chunks of code do exactly the same thing. Ports are just like queues. However, they have to abide by two rules. One is that any Ractor can write to a port. So any Ractor can write to a port. And here is the mind-bending rule. Only the creating Ractor, only the Ractor that created the port can read from it. So this is kind of like, takes a second to wrap your head around. So only the creating Ractor can read, and I'm showing an example here. On the left, this example works fine. We create a port, we pass in the main Ractor, we pass it to a child Ractor, and we're allowed to write to that port. And the main Ractor is allowed to read from that port because it created it. Now, on the other hand, if we created a port on the main Ractor, but we pass it to a child Ractor and we try to read from it, you'll get an exception. It doesn't work. So these are kind of the rules that we have to play by. Of course, if you're coming from the threaded world, this may require some like mental shifts. I know it did for me. And here's an example of threads. These threads are all sharing references to exactly the same queue. So we have many threads, and they're referring to the same queue. We're trying to read, each child thread is trying to read from that queue. But if only one Ractor is allowed to read from a port, how can you write this code example? How can you do this? It's a little bit more complicated in the Ractor world, and I want to show you how we can accomplish this. In the Ractor world, we create a rendezvous point. I don't know the right name for it, but I call it kind of a rendezvous point or a coordination point for producers and consumers. So first we have a coordination point. This Ractor is in charge of collecting work from producers and handing that work out to consumers. So in this case, we'll have a coordinator. It takes the work in, and then it hands that work out to the consumers. The biggest difference between this and the queue-based system is that all of the worker Ractors have to specifically ask for work rather than pulling the work. So here we say, our coordinator says, hey, I'm going to wait for the next Ractor that wants work, and as soon as I get that Ractor, I'm going to give that Ractor work. So each of the child Ractors has to ask for work. So here are what the workers look like. Our workers say, hey, coordinator, I need work. I need work. Please give me something to do. The coordinator will give it work. It sits here and waits until the coordinator gives it work, and then it does whatever it needs to do. So it's a little bit more complicated setup than the queuing system, but what's nice is there are no locks or mutexes. We didn't have to write synchronize anywhere. That's not a thing. There is no synchronization. There are no deadlocks. And what's really even better is that we get CPU parallelism in pure Ruby code. One more feature. I want to show one more feature, and I think this particular feature is especially interesting to Rails developers. So I was talking about how mutable data gets copied. Like, let's say, for example, we have two Ractors. One Ractor creates a string. It wants to pass that string to a second Ractor. When that happens, it copies the data. Now, there's one exception to this case, which I think is a very interesting exception. And that is that the Ractor return value is not copied, but only once. And I'm going to show you an example to make this a little bit more clear. Let's say we have a Ractor like this. We're creating a Ractor R. This R Ractor allocates object O. We're going to print out the object ID and the frozen state of the object. R returns the object O. And then our main Ractor will try to read that object, get it, and then it's going to print out the object ID and the frozen status. And if we do that, we'll see that these objects are identical. Oh, no. Oh, no, it's the same object. All right, I'm going to do the next slide. I'm sad. My little thing didn't line up. Anyway, if you run this code, you'll see that neither of them are frozen. They're not frozen. However, the object IDs are identical. So that means that we were able to pass a mutable object between two Ractors without doing a copy. So why is this interesting? Why would any of this be interesting to us as Rails developers? I am going to tell you. Why did I ask that? I'm going to tell you why. It's a rhetorical question. Let's talk about it. So, yes, I'm nervous. What is one use case for C extensions? There is a use case for C extensions. Usually, we're using C extensions to bind to native libraries, like libxml is binding for, or Nokogiri is binding for libxml. Of course, there are many other C extensions. There is another use case, and that other use case is for releasing the GVL. In C extensions, we actually have a way where we can release the GVL and do other work. So a good example of this is the bcrypt gem. So bcrypt is written in C, the bcrypt gem is written in C. We have these three lines are in the bcrypt gem, and basically what they're saying is, hey, I want to call this function, but I want you to release the GVL, then call the function, and then acquire the GVL again. So what this means for us is that we're calculating password hashes without holding the GVL. So let's say, for example, you're using Puma as your web server. Somebody goes to log into your application. You start calculating that password hash. While you're calculating the password hash, Puma is able to service another request in parallel. So we're able to get CPU parallelism in C extensions by releasing the GVL. What's nice about Ractors is we can kind of think of them as a no GVL block. So let's imagine that we had bcrypt written in pure Ruby. Let's imagine that was pure Ruby and not C. We could write something like this, where we create a new Ractor, we calculate bcrypt, and we return the value of bcrypt. And we can think of this as kind of just a no GVL block where other threads can run. We can have our Puma web server, and it can serve up requests while we're calculating bcrypt, doing exactly the same thing that the C extension did, but we were able to write it in pure Ruby. So maybe not calculating bcrypt. A real-world example might be just parsing JSON, for example. Like maybe you have an API server, you're spending a lot of time parsing JSON, throw it in a Ractor, and now all of a sudden you can do other requests in parallel while you're parsing that JSON. So this seems like a very low-effort way to start introducing Ractors into your system and get some parallelization, but without necessarily having a Ractor-based web server. So one thing I would like to pitch to all of you is when you upgrade to Ruby 3.5 in the future, and you're going to do that right away, right? Yes, yes, yes. Try wrapping your CPU-intensive code inside of a Ractor and see if that is able to help out your parallelism. Of course, do this in Ruby 3.5. So another thing I want to talk about here is like weird bottlenecks that we've had to solve. So we've been trying out Ractors, fixing crashes, trying to improve the API. But I want to talk about a weird bottleneck just because I think it's very, very fun and interesting. So somebody filed an issue on the Ruby bug tracker, and the issue, I'm just going to give you a summary of the issue. The issue is parsing JSON is slower in Ractors than if I do it serially. So if I try to parse JSON in parallel, it's actually slower than if I just tried to do one at a time. And we've fixed this bug. We've since fixed this bug. But I want to tell you the problem because I think it's a little bit surprising and interesting. Yes, we fixed the bug. Nice, yes. John fixed the bug. Great job, John. So here is a problem. When we parse this JSON here, we get a hash back. And the key to the hash is a string. And interestingly, both of these strings are exactly the same object, right? They're exactly the same. They have the same object ID. They get deduplicated when we parse JSON. And we have to do this deduplication when we're doing it inside of a Ractor as well. So both of these, when we parse the JSON here, we check that key's object ID. We'll see, this is indeed the same object. And the way that this is implemented internally to Ruby is we have something called an fstring table. I think it stands for frozen strings because these strings are frozen. But this fstring table is essentially a global within Ruby. And we have to consult this global hash table in order to resolve those keys to be exactly the same object. So while we were doing multiple Ractors, these Ractors had to take a lock on this fstring hash. So we're ending up getting lock contention on this global hash table within the internals of Ruby. And you wouldn't know this necessarily just from looking at the Ruby code itself. The solution to this was to turn the fstring table into a lock-free hash, which John was able to do. And once he did that, JSON parsing got 12x faster. So we should, yes, round of applause. Do people here parse JSON? Is that a thing? Now, unfortunately, the fstring table is not the only thing like this we found within Ruby internals. Also, we have a global table, an ID table. This is for symbols. So symbols get resolved into the same object, so we had contention there. A thing called the CC table, which is for inline caches. Whenever we needed to create an inline cache or look up an inline cache, we would end up locking. Another example is the encoding table when we're looking up string encodings. So internally to C Ruby, we have all of these global data structures that you wouldn't necessarily know are global while you're writing Ruby code. Anyway, the point is that our team is trying to find these bottlenecks and fix them, figure out how we can remove these bottlenecks so that when you upgrade, we can actually start using Ractors for real in production. The next thing I want to move on to, I'm going to move on to the next topic now, which is ZJIT. ZJIT is a new compiler that we're going to be shipping with Ruby 3.5. So I want to talk a little bit about the work that we're doing on that. And I want to talk about what are JIT compilers in general, because people have asked me this. We'll look at the differences between YJIT and ZJIT, and then I want to give some tips for Rails developers on how you can write more JIT-friendly code in your application. So the first thing is that before we get to the meat of this JIT section, I kind of want to define a term which was confusing to me when I first started working on JIT compilers. Ruby's virtual machine is called YARV, and it's what we call a bytecode interpreter. So it's interpreting the bytecode. When we compile your Ruby code, we turn that into bytecode. That bytecode gets interpreted, and we have a virtual machine that interprets that bytecode. So if anybody, namely me on the stage here, refers to something as the interpreter, what they mean is this virtual machine that's interpreting that bytecode. So what is a JIT? I think this is an important question to ask because I think there are a lot of definitions for what a JIT compiler could be, but to me, a JIT compiler is something that assembles code at runtime and assembles machine code at runtime and is usually as lazy as possible. So here's an example of something that could be considered a JIT compiler. Here we're saying, hey, we're not going to define the adder accessor right now. We're going to wait until method missing gets called. And then when method missing is called, we're going to define the adder accessor. So here we'll say we'll just define that. And then the next time the method is called, we don't call method missing anymore because we generated this code at runtime. So we could kind of think of this as a JIT compiler. Of course, we wouldn't actually write this in our code, right? Please don't. But this is an example that could be considered one. So we generate code at runtime. I think of them as generating code at runtime. They're usually lazy. We try to be lazy about it, meaning that they're late. They're kind of late. They do it later. Another important aspect is that they should speed up our program. This is, unfortunately, I have written JIT compilers that do not speed up programs. So yeah, I think this is an important aspect. Another question people ask me are like, how can a JIT speed up our code? Like, how can it do that? The JIT compiler has to generate code that does exactly the same thing as our program did originally. If it's doing exactly the same thing, how can it possibly be any faster than our bytecode interpreter? So I want to talk about that a little bit. The JIT and the interpreter must match, as I was saying. Whatever code the JIT compiler produces, it must have exactly the same behavior as the interpreter. So how can we fix anything? One thing that we can do with a JIT compiler is that we can eliminate the interpreter overhead. So this interpreter has overhead, and typically when we're running a program in Ruby, we'll have something that looks like this. So we have our CPU, we have YARV, which is our bytecode interpreter, and on top of that, we're running our Ruby code. The interpreter is running that Ruby code on the CPU. YARV is a C program, and that C program is running code on your actual CPU. The way I think of a JIT compiler is it's getting rid of this YARV step here. It's basically promoting your code to running directly on the CPU. I can kind of think of this as like, well, you're running your code inside of a Docker container, but somehow you're able to escape that and instead of running inside of a container, you're running on the bare metal itself. And the JIT compiler is just doing that at runtime for you automatically. The other way that we can speed up programs is by caching values. So here's an example. Again, back to our Fibonacci sequence, because that's what we do, speed up Fibonacci. We have an example here of the number 35, and you can see if we look at the YARV bytecode, we have a literal 35 in there. We have that number. What we can do in the JIT compiler is we can say, hey, I'm going to actually embed that number directly into the machine code. So when we compile this, if you were to disassemble the machine code, you might see something like this, where we have the number 35 directly in there. So that's another way that we can speed this up, is rather than loading that 35 from memory, we already have it in the machine code. Another thing that we can do is speculate. We can speculate on values. And we're able to do this in a way that the interpreter cannot do. So let's say we have code that looks like this, sum 2 plus 5. Our JIT compiler might say, hey, you know what? I don't think anybody is going to monkey patch plus, hopefully. So in advance, what it can do is it can say, I'm just going to add those two numbers together. We're going to get the number 7, and we're just going to keep that there and return that rather than executing the plus value itself. But what's cool, a cool thing a JIT compiler can do that our interpreter can't do is it can deoptimize this. So let's say somebody does monkey patch plus. Like it did that. It did the constant folding, and then all of a sudden somebody monkey patches plus. Our compiler can detect that and say, oh, you know what? I messed up. My speculation was wrong. I'm going to fall back to this particular implementation. So I'll just go back to calling plus on the number and then do whatever the interpreter would have done. Another thing we can do is we can eliminate type checking. Yeah. Everyone, wait, who likes type checking? Yeah, type checking. Well, we don't have to. We don't have to do it. We can eliminate this type checking. This is a different type of type checking. I'm going to explain this here. When we have code like this, our friend Fibonacci again, when we have code like this, when it runs, we have to check, like, okay, when we do this comparison, is n an integer? The interpreter has to check this. Is n an integer? If so, I'm going to do an integer comparison. And then when we do minus, it's like, oh, is n an integer? If so, I'm going to do minus in both of these cases. In our compiler, we can say, well, I know that n is an integer on the first one. I did that test. I was able to do that type check. And now there's no reason for me to do it later on in the program because I know for a fact that n is an integer. So it's able to eliminate these two particular type checks. So these are different ways that a compiler can speed up the code that an interpreter cannot do. So let's take a look at YJIT and ZJIT and how they work and the differences between them. Who is using YJIT in production? Anyone? Yeah, oh my gosh, so many people. That's awesome. Thank you. That's great. All right, YJIT is a lazy basic block versioning compiler, or LBBV. Of course, this already ships with Ruby. You all are using it. Many of you are using it in production. YJIT uses a technique that was pioneered by Maxime, the author of the JIT compiler, in her PhD thesis on lazy basic block version. So I'm going to describe how this compiler works and then move on to ZJIT, the differences between that and ZJIT. So this is how LBBV works in action. LBBV, this compiler, discovers basic blocks lazily. And what a basic block is a straight line of code that has no jumps in it. So no if statements, nothing like that. So it's just code until we find an if statement. That is a basic block. So in this particular example, when we compile the add method, what YJIT will do is it'll go here and it'll say, hey, I'm going to compile y equals 0. And all of a sudden it gets to the if statement and it's like, oh, this is the end of a basic block because it could jump between one of these branches. So it compiles that basic block, and then it waits. It basically waits. And it says, which side of this if statement am I going to execute? Let's say it executes this side of the if statement, the top one. In that case, it'll compile that side of the if statement. It'll create a new basic block until there's another jump again, which is after that. We'll create a third basic block down here that's just return y. So we end up with something that looks like this. So we compile like that. And one thing to notice is that this code right here, it never got compiled. We didn't compile it because we didn't actually use it. That never happened. So what this means is YJIT gives us really, really fast warm-up because we're compiling as little code as possible. Another nice thing is that we have low memory overhead because we're compiling as little code as possible. And we also have low overhead on type discovery. So what I mean by this is when YJIT pauses at those particular locations, it's able to look at all the values on the stack and say, oh, n, that's an integer. I know that's an integer. And then generate code that's specific for that integer. Some of the downsides of YJIT, though, are that its register allocation is a little bit harder. Whenever we're dealing with variables in our program, we want the compiler to keep those variables in registers, and that's because registers are faster to access than memory. So we would really, really want to keep those values inside of registers. Unfortunately, registers are a finite, it went too far. Registers are a finite resource, so we can't just put all of our variables in registers. We have to only put some of them in registers some of the time. So an issue is, like, let's say we're compiling this code with YJIT. I've rewritten the code a little bit here, but the functionality is exactly the same. Let's take a look at this. We have y0 at the top. We're defining two other variables, y1, in both branches of the if statement, and then we return y1 at the end. So let's say YJIT compiled this, and we turned this into machine code, and we decided that this value, y0, should go into the x0 register on my crappy ARM machine. So we put it in there, and that's where we decide to put it. Now, when YJIT goes to compile the other branch, like let's say we execute this code again, and we want to compile the else statement, right here, the question is, which register do we use? We have to maintain the knowledge that that other side of the if statement used x0 for the value of y1. And this is actually a very, very difficult problem. This particular case, this if statement, is a big problem in compilers and one of the main things that folks focus on. So the way that we handle this in YJIT is we actually just end up writing these local variables into essentially known locations in memory. They're written to known locations. So rather than keep track of all the registers, we just basically treat it as if it has an infinite number of registers where those registers are essentially just memory. So I'm not going to get into the details, but as we discussed, reading memory is not as fast as reading registers, so we'd prefer to keep things in registers. So comparing this with a method-based compiler is a little bit different. It can say like, oh, okay, I'm just going to look at the entire method. And it'll compile both sides of the if statement. And because it has the context of all the variables used in either side of those if statements, it's able to figure out, like, oh, OK, in one side we stored y1 in x0, so we're going to do the same thing in the other side, and then all of our code works together. So we're able to keep those values in registers 100% of the time rather than spilling them to memory a lot of the time. So another nice thing with method-based compilers is it's a little bit easier for us to fold constants. As I said, we can do more efficient register usage. The other thing is it's easier to learn a little bit. A lot of the compiler documentation out there, they focus on method-based compilers. You can use traditional resources for compiler theory on a method-based compiler. Now, the downside, though, is that it might compile too much code. As we saw earlier, like if we don't take one side of that if statement, a method-based compiler is going to compile it where YJIT would have done nothing. Another downside is that tracking types is a little bit harder. We're not really pausing in the actual code with a method-based JIT. So what we have to do is we have to start tracking types as the interpreter is executing. So we had to add some infrastructure for tracking types. So I guess the idea with ZJIT was we thought, what if? What if we could take what we had learned from YJIT and like how to actually put a JIT into C Ruby, how to deploy it, how to do development on a JIT compiler, how to make it low overhead. What if we could take all of those techniques and apply those to a method-based compiler? And that's where we came up with the idea for ZJIT, a next-generation JIT compiler, which is essentially our method-based JIT. Now, I am very, very excited about this work. However, I would like to temper your expectations a little bit. It is very, very new. So if I can make a humble request that you lower your expectations of this JIT compiler a little bit lower. This is probably good. It's not rock solid at the moment. If you go check out Ruby Edge and you try to run Ruby Edge in production, like all of you are going to do after this presentation, right? Yeah. Yes. You can use ZJIT if you do ruby-ZJIT, but it's probably not going to be as fast as YJIT. Wait, no, not probably. It will not be as fast as YJIT, but we are going to get it there. So with that said, I want to talk about like what can I do today? Like, what can I do today to write JIT-friendly code? So as a Rails developer, why do I care about this, and what can I do about it? Now, me working on compiler stuff, I really want to say to you, write whatever code that you want. Because the idea is, like, you should be able to write any code that you want to, and then we'll just figure out how to speed it up so that you don't have to change anything. But that is theoretically how things should work. But the truth is that some patterns are easier to speed up than others. So otherwise, like, why bother profiling your code? Just wait for the newer version of Ruby. But sometimes we do want to speed things up. There's an opportunity cost. So you can wait for us to improve the JIT compiler, or you can write code that is a little bit more friendly and have those speedups today. So do you want to wait, or do you want to have speedups today? And I'm going to give you one. I said I was going to give you pro tips, but I'm going to give you just one pro tip. We are going to monomorphize these pro tips. Thank you, Ufuk. Yes. So we're going to talk. Thanks. We're going to talk about monomorphizing call sites. This is a very dumb compiler joke. I'm so sorry. In order to describe to you what this is, first I want to describe polymorphic call sites. We're all familiar with polymorphism, right? We use polymorphism every day. Yes? Yes, we write in OO. Polymorphism is great. Here's an example of a polymorphic call site. So we have two classes, A and B, and we're passing instances into call foo. We call foo on the thing. This is what we call a polymorphic call site, and we call it polymorphic because it sees different types. So computer vision's getting really good. It's able to see them. So here we have an instance of A and an instance of B, both passed to the same method, and this thing calls a method on two different types. Now, we'll compare this with monomorphic. All monomorphic means is that it just sees one type. So it's just one versus many. So in this case, we only see one type here. It's a monomorphic call site, so because it only ever sees that one A type. So if you have a polymorphic call site and you JIT compile that code, the JIT code is going to end up with a whole bunch of tests saying like, OK, is this an instance of A? Is it in class A? Is it an instance of class B? Is it an instance of class C? Et cetera, et cetera, et cetera. So the more types that you see there, the longer it's going to take to find that particular method and call it. So if you can monomorphize that call site, make it only one type, you can actually speed up that call site very nicely. And I have an example, like a real-world example of it today. Here, we had a pull request for visitor methods in Prism, and we were able to see a 13% speed improvement over Ruby 3.4 by monomorphizing call sites inside of Prism. And this isn't even with the JIT compiler. This is just with the normal interpreter. So this particular pro tip will work for you whether you're using YJIT or not. So the other thing is, it's not just about types, like which class you use. It's also about instance variables as well. So we can think of this here as a polymorphic instance variable read, because depending on the branch that you take and initialize, you'll end up with two different shapes. So the order in which instance variables are set actually matters. So the thing that I want to convey to you is, like, I don't want to say to you, don't use polymorphism. Polymorphism is terrible. I think it's great. I really think it's great. But what I want to convey is you should use useful types. Set instance variables in a consistent order. So try to set all of your IVs in a consistent order. Don't randomly set them. When I say useful types, like, what does that mean? What is a useful type? When I say useful, I mean useful to your application. So something that actually provides you with value. So for example here, like maybe you have multiple different credit card processors, and you want to have some sort of strategy object that changes depending on the type of credit card processor or payment processor backend that you're using. So in this case, we have an example where polymorphism is really helping out our application. It's encoding business logic. It's making the code easier to understand and easier to maintain. This is something that should be like celebrated and something that we should be doing in our code. When I say like low-value polymorphism, what I'm talking about is code that looks kind of like this, where we've got a cache, and we're passing a key to the cache, and we're just calling 2s on that thing. And the reason we're calling 2s on that thing is because we want to take either strings or we want to take symbols as our inputs, and we need them to be consistent when we look it up in the cache, so we're just calling 2s on that. So I don't really think that this type of code is, this is my very hot take on stage today. I don't think that this type of code is very valuable, because like what are we actually getting out of this? You could just change the caller to use a string instead. So we could say, oh, instead of using a symbol here, let's just be consistent and always use a string in this case. Or even better, you're like, no, Aaron, I need to use a symbol there. I have to. Got to use a symbol. We don't know where the data is coming from. It could be a symbol. We need to make it a symbol. So maybe instead of doing the 2s here, we could actually change the caller and say, well, let's just call 2s in this case. And if you do that, you're ending up with two monomorphic call sites. And of course, well, since it's always a consistent type going into the lookup method, we can just remove the 2s and say, well, now we only have a single monomorphic call site. So this is the type of, like, in my opinion, low-value polymorphism that we should be removing from our applications. A famous person once said, keep useful polymorphism, remove useless polymorphism. Love quoting myself. All right, let's wrap this up. We talked about Ractors. We talked about parallelism. We talked about weird bottlenecks, which I thought were very, very fun. We talked about how Ractor new can be thought of as a no GVL block. We talked about JIT compilers, how and why they work. We talked about the differences between ZJIT and YJIT, as well as writing JIT-friendly code by monomorphizing our code. So I want all of you to please upgrade to Ruby 3.5 now, right now. I'll wait. I know we have a party coming up. Oh, hold on, one more thing. I have a question for all of you. Do you allocate objects in your Rails app? Yeah, object allocate, yes, let's cheer on object allocation, woo! Uh, I love asking questions that I know the answer. Like, yes, we allocate, woo! Allocations are much, much faster in Ruby 3.5, which is, I hope is a good reason for all of you to upgrade. I want to show you a benchmark. We made them faster. Here's a benchmark. We have a user class here, and we're going to instantiate it 500,000 times. We actually made this 70% faster on Ruby 3.5 than it is in Ruby 3.4. So please, please, please upgrade. It's been an honor to be here with you this year. I'm so happy I could come to Amsterdam. Oh, wait. I have one more joke. So I was going out to dinner here in Amsterdam, and I was really, really worried whether or not they would split the bill for me. But it turns out that everybody here is dining Dutch. Oh, come on. All right, thank you.